What specific problem does the DPMC algorithm aim to solve in the context of inverse problems, and how does it build upon the limitations observed in the diffusion posterior sampling, DPS?
The DPMC algorithm aims to solve the problem of accurately restoring data, X, from degraded measurements, Y, in the context of inverse problems, particularly when dealing with high noise levels that can lead to poor sample quality. It builds upon the limitations of the diffusion posterior sampling, DPS, by addressing the inaccuracy of the posterior approximation, PY(X_T), approximately PY(X_0), at higher noise levels, where the distribution can become multimodal and the estimation, (X_0), may deviate significantly from the true, (X_0). DPMC introduces annealed Markov chain Monte Carlo, MCMC, sampling to improve the posterior approximation by leveraging a sequence of intermediate distributions, allowing for better exploration of the sample space and reducing the error in the posterior estimation. This approach enables DPMC to generate samples that capture more vivid details, compared to DPS, which often produces blurred results under similar conditions. Ultimately, DPMC empirically outperforms DPS across various inverse problems by effectively managing the challenges posed by noise and the ill-posed nature of the restoration task.
How does the proposed DPMC algorithm work? Illustrate it step by step, detailing the proposal stage and exploration stage of the annealed MCMC sampling process.
The proposed diffusion posterior MCMC (DPMC) algorithm operates in two main stages, the proposal stage and the exploration stage. In the proposal stage, given samples, X_T, that follow the intermediate distribution, P_T X_T, Y, the algorithm first denoises these samples to T1 using the standard diffusion step, resulting in proposed samples denoted as X_T1. This step aims to provide a good initialization for the next intermediate distribution, P_T1 X_T1 Y. In the exploration stage, the algorithm encourages the proposed samples, X_T1, to explore the landscape at noise level, T1, and follow P_T1 X_T1 Y through MCMC updates. Specifically, Langevin dynamics is employed as the transition kernel, iteratively updating the samples starting from X_T1 to refine them according to the target distribution. This two-stage process allows DPMC to effectively bridge the gap between the noise distribution and the target distribution, enhancing the quality of the generated samples in solving inverse problems.
Can you provide a simple yet illustrative numerical example to explain the workings of the DPMC algorithm, particularly focusing on how it processes the samples through the intermediate distributions?
To illustrate the workings of the DPMC algorithm, consider a scenario where we have a noisy image sample, Y derived from a clean image, X through a forward measurement operator, A with added Gaussian noise. Let's say we start with a noisy sample, Y, and aim to restore X using DPMC. The algorithm first defines a series of intermediate distributions, P_T X_T, Y, for T equals 1, 2 L.T, where T is the total number of noise levels. For example, at a moderate noise level, T, the algorithm generates a proposal sample, X_T1, by denoising X_T using the diffusion model. This sample may not fully adhere to the target distribution, P_T1 X_T1 Y, but it serves as a good initialization. The next step involves applying MCMC updates, specifically Langevin dynamics, to iteratively refine X_T1 towards P_T1 X_T1 Y. This process is repeated for each intermediate distribution, allowing the samples to transition smoothly from the noise distribution to the target distribution, ultimately leading to a high-quality restoration of X that captures more vivid details compared to traditional methods like DPS. Thus, through multiple sampling steps at each noise level, DPMC effectively bridges the gap between the noisy observations and the desired clean image.
What are the theoretical or empirical advantages of using the DPMC method over existing alternatives like DPS or FPS, particularly in terms of sample quality and efficiency?
The Diffusion Posterior MCMC DPMC method demonstrates several theoretical and empirical advantages over existing alternatives like diffusion posterior sampling DPS and filter posterior sampling FPS. Theoretically, DPMC provides a more accurate approximation of the posterior distribution by leveraging annealed MCMC, which allows for smoother transitions between intermediate distributions, thus enhancing sample quality, especially in high-noise scenarios where DPS may produce blurred results. Empirically, DPMC outperforms DPS across various inverse problems in the image domain, achieving better sample quality as evidenced by lower LPIPS and FID scores, while also requiring fewer evaluations, NFE, compared to DPS. Additionally, DPMC's approach of applying multiple MCMC steps at each noise level leads to a constant improvement in performance, making it more efficient in generating high-quality samples. Overall, DPMC effectively fills in meaningful content that aligns with noisy observations, addressing the challenges posed by the ill-posed nature of inverse problems more robustly than its predecessors.
What experimental validations were performed to test the effectiveness of DPMC, including the datasets, benchmarks, and metrics used for comparison, and what were the key findings?
To validate the effectiveness of the Diffusion Posterior MCMC DPMC algorithm, experiments were conducted on the FFHQ and ImageNet datasets, utilizing 1,000 validation images for each. The DPMC algorithm was tested against various inverse problems, including super-resolution, random inpainting, deblurring and phase retrieval, with Gaussian noise set at sigma equals 0. 05. Key benchmarks for comparison included the original diffusion posterior sampling, DPS, filter posterior sampling, FPS, and other methods like denoising diffusion restoration models, DDRM, and alternating direction methods. The performance was evaluated using metrics such as LPIPS, which measures perceptual similarity, and FID, which assesses distribution differences between generated samples and observations. The results indicated that DPMC outperformed DPS in terms of sample quality across all tasks, achieving similar or better LPIPS and FID scores while using fewer evaluations, demonstrating the effectiveness of incorporating MCMC in the sampling process.
What specific limitations or potential drawbacks does the DPMC method have, especially in relation to noise levels, model complexity, or when applied to different types of inverse problems?
The DPMC method, while effective, has specific limitations related to noise levels and model complexity. At higher noise levels, the approximation of the posterior distribution can become inaccurate, leading to potential challenges in capturing the true underlying data distribution, as indicated by the multimodal nature of the posterior. Additionally, the DPMC algorithm requires a careful selection of intermediate distributions and MCMC sampling steps, which can increase computational complexity and time, particularly if too many intermediate distributions are used. Furthermore, while DPMC performs well on linear inverse problems, its effectiveness may vary when applied to nonlinear inverse problems, as evidenced by the need for careful initialization and the dependency on the quality of the generated samples. Lastly, the reliance on MCMC sampling may introduce variability in results, which could affect consistency across different types of inverse problems.